Okay, we'll begin today by looking at an alternative to finding these confidence intervals and also do a quick hypothesis test for the standard deviation. So this was a problem that was done. It says a study found body temperatures of 106 adults, and the mean was given as 98.2, and the sample standard deviation was 0.62. They want us to find a confidence interval for sigma. And so this was the solution that they came up with. They came up with first collecting the statistics, and then they established their alpha, and then they also figured out what their areas are for this thing. So I don't know if you're familiar yet to use the table A2. You will need to do this in your homework. But if this was the problem, and this is, remember, this is a confidence interval problem, and so we have to get those two things straight, a confidence interval versus a hypothesis test. A confidence interval is always going to be two-tailed, because it has a greater than or equal to, or greater than or less than sign and another less than sign. So it's always going to be two-tailed. So if your confidence interval is supposed to be 95% confidence, then your alpha is 0.05. You have to cut that in half and then have the tails, have the area under the tails as 0.025 on one side, and the area on the other side is 0.025. But if the area on one side is 0.025, then the area on the other side is 0.025. This table is going to ask us, if you're looking for a specific number, what is the area to the right of that value? So if we take a look at this first one over here, I don't know if this would be considered the first one, but this has an area to the right of it as 0.025. And so I would go to 0.025 and look down with our significance or the degrees of freedom. It's 106, so the closest number that I can find here is 100. And so that's it gives you a point of 129.561. And that's your chi-square right. This is your critical value on the right side. Now, chi-square left has an area to its left as 0.025, but remember that this table is looking for the area to the right, so 1 minus 0.025 is 9.975, and so you have to look at 0.975 on this table and down to whatever the degrees of freedom is, and that gave us 74.222. So once you know those critical values, chi-squared right and chi-squared left, you put them into that formula, and then you come up with a confidence interval. Now that we have these programs in here, we would be able to do this without having to rely on the table, without having to look for the critical values and stuff like that. So that's what I want to do now. So let's pull out your calculators that have their new programs all figured out. So the way to run a program in your calculator is right in the middle, right under stat, is PRGM, program. So let's click on that. And then you have the first choice on top is EXEC, which is to execute. And then next is edit, and then the last one is new. So you don't want to mess with these things, so never go to edit. And if you want to mess around to try to write a program, you can go to new. But most of the time, you'll just be executing these programs. So for this particular problem, our program is CI, that stands for confidence intervals. SDEV is standard deviation. So go down to select that and click enter. And then it's going to say program CISDEV. Do you want to run it? It doesn't say that, but that's what it's doing. So you just press enter again, and now we're in the program. Okay? So now that we're in the program, what we're going to do is we're going to take a look at what they're asking for. They're asking for N. That's your sample size right here. So let's just, it's 106, so let's type 106 in. Enter. The next thing they ask for is S. So somewhere along the line, you'll need to figure out what S is equal to. In this case, our S, our standard deviation for the sample, is 0.62. So let's type in 0.62. And then press enter. Oh, and then I guess we do still need to figure out the table. Okay. So enter chi-square left. So chi-square left is 74.222. 74.222. And then enter the chi-square right, which is this one, and that's 129.561. All of a sudden, I'm not so interested in this program anymore. I didn't think you needed to look for the chi-square values. In any case, this is our result. Our sigma is between 0.558, that's basically what they have here, 0.56, and then 0.737, which is basically what they have here, 0.74. All right, so you do need to figure out the critical values. Any questions? There is a program to find a critical value. Should we do that? I suppose we should do that. Esmeralda, did you get the programs from Frank? Can I have your calculator? Michael, did you get your? Bring it up. So what's the program called to find the critical number? Inverse chi-square. All right, let's talk about how to use this inverse chi-square business. So it looks like this little bit of analysis down here where you have your alpha, and then if you know that it's a two-tail, then you have to split that alpha in half, 0.025 and then 0.975. And so let's go to our calculators and try to inverse chi-square values. Program inverse chi-square, hit enter. Enter the degrees of freedom. So we have n is equal to 106. Our degrees of freedom would be 105. And if we really want to get exactly what the chart has, it's the degrees of freedom they have is 100. But I don't think it'll be that much of a difference. Did you guys get this? How about those people who downloaded from Frank? Did you get this? Same thing? Oh, maybe you have to find this. I just hit it again. Oh, okay. Area to the right. So if we choose this first one, 0.025, that should give us a value. One thing to note is that when your calculator has this thing on the side, that means it's thinking. So give it a minute. If after 5 minutes it's still not doing anything, then you might have to stop it because it might have got caught up in a loop. But sometimes some of these calculations, especially when it deals with the chi-square, it takes a little while. So hopefully it'll find something. So our answer for this should be chi-squared, the area to the right. It should be 129. Still going. Anybody's calculator stopped and found something? Oh, I'm done.
How do you know that the 0.025 is right?
I think the best thing to do is to draw a figure like this. If you know that your alpha is 0.05 and you're dealing with a confidence interval that's going to be split up into two tails, then you have to take 0.05 and divide it by 2. And then you get an area to the right and then area over here to the left. Yeah. Well, we use 105, so if we actually use a chart, let me try this again, or you guys can all try it again. Let's try it again with 100, with our n is equal to 100. But I think if you were to use the 135 that we got, I don't think that will be much different from the answer. It might be off by like 4 at the 4th or 5th decimal place, but usually they ask for these things in 2 or 3 decimal places, and it might be okay. Maybe. No, maybe not. So we're still waiting for this one. Hopefully this one will turn out to be 129. Yeah. So this one is 129.561. I didn't think that was going to be that big of a difference. Okay. So that's 2 of the problems that deal with a chi-square distribution. And again, I encourage you to take a look at the videos that discuss these things. I think my videos are all over the place right now. But I'm going to continue to use iTunes U for everything, and then these new ones I'll start uploading it in YouTube as well. Oh, the other one, you still have to do that work where if the tails got split up, if 0.05 got split up, that means the area on the left side here is 0.025, and you need 1 minus that. So the complement to figure out what the area to the right is. So we could do the same thing. Let me run this program one more time. So I'm going to use their number again for the degrees of freedom, 100 instead of 105. Then find it. So this time the area to the right is 0.975. And then we'll run it. So maybe if anybody wants to give it a try, do the degrees of freedom to be 105 to find those critical values. I think one of them was 135 point something. You could do the same thing here to find a critical value for this, and then try to use those critical values to put it into the CISDEV. Yeah, so this one came out to be pretty much like what they have in the table, 74.2219, so 74.222. Okay, so that's Chapter 7 stuff. Chapter 8 homework is due tomorrow, and most of those videos are online, but I wanted to redo the confidence interval, the hypothesis test for the standard deviation. So let's take a look at that. No, this isn't what we did. Well, why don't we just do another homework problem? So 8-6. So the nice thing about this is that it gives us a p-value as well. So the big thing about the p-value is that we don't have to rely on using the traditional method where we compare it to a critical value, which means we don't have to find the critical values for these problems if we're using the p-values. So that's one nice feature for this particular setup. All right, so this one, I think we need to do a little bit of legwork to try to figure out what the standard deviation of this thing is. So let's do this. And do this on another sheet, piece of paper, or whatever. I think I'm going to use OneNote. So this is our example. Is it readable? So we need to get some initial information out of this thing. The listed values of wait times for customers of a bank. Blah, blah, blah. Test the claim that the standard deviation of wait time is less than 1.7, which is the standard deviation of wait time at the same bank when separate waiting lines are used at each teller window. Use a significance level of 0.05, and then they ask you the question, does a single line appear to reduce the variation among wait times? So it's a comparison of standard deviations. Let's go through the motions now of the hypothesis test, since that's what we're dealing with. What is the claim? Is less than 1.7. So these are the words to describe our claim. How would we write this in symbols? Sigma is your standard deviation. That's the very first important step, is to figure out which symbol you're using. So sigma is, well, it's less than 1.7. All right? So the opposite of this is greater than or equal to, or you can just say equal to. So we get our setup for H naught and H1. Sigma less than 1.7, does that go into the null hypothesis or the alternative hypothesis? The alternative hypothesis. It does not contain a condition of equality, so it goes into the alternative hypothesis, and I'll remind myself that this is the claim. The opposite, well, we can do it a couple of different ways, and the more standard way that people use is sigma is equal to, but you can also say the exact opposite of that, which is greater than or equal to. So if we're dealing with a claim as being the alternative hypothesis, then you can make your null hypothesis just a regular equal sign. We have significance level of 0.05. And then the other piece of what we need to do is we need to figure out our sample statistic. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 of them. And we're going to need our S. And we can make note of our X bar, our mean, but we're not going to need the mean in our calculations. So I'll just leave it like at that. And for this one, we'll need to pull out our calculators to actually compute the standard deviation from these numbers. So let's go to Stat and edit a list. I'm going to go up to L1 and clear it and put in these values. And just to make sure, I go in my last one and figure out my count here. I have 10 of them. The L1 parentheses 10 tells me that's my 10th element. And if I just scroll back, 10 isn't so much, so this is easy enough to double check to make sure that we got everything correctly inputted. All right? I just scrolled back up to make sure, and I looked at these numbers to make sure that which other numbers? Oh, that doesn't matter. Those are insignificant right now. Okay, and then let's just do a quick one var stats on L1, and hopefully we're all getting the same thing. And remember to look at the S. X, right? Not the sigma, but the S from your for your standard deviation. So our S is 0.723. And I'll probably, I was going to say I'll go one more, but the next digit is a 0. Or maybe I'll just put a 0 there anyways. It looks like we're going to want our answers, our test statistics. If they were asking for a test statistic, we would want that to be rounded off to like 2 decimal places or something. So it's always good to go a little bit extra. All right. So now this is where we would normally pull out our formula and then find our test statistic and compare it to our critical value. But instead, we're going to go straight to our calculator with our new program called Test SDev. So that's a test for the standard deviation. And let's press enter, program test dev, and the first thing they ask for is to figure out what your n is equal to. So n in this case is what, 10? Notice that you have to be careful, make sure you answer what they're asking for. Sometimes they ask for the degrees of freedom, df, sometimes they ask for n, so you make sure you're putting in the correct value. So the degrees of freedom is 9, but they're asking for n itself, so that would be 10. Enter the standard deviation. Our standard deviation is 0.723. That's for the sample. And then the next one is the S, or the sigma, sorry. Next one is the sigma, and that is from our hypothesis, our null hypothesis, so that's 1.7. So like in those other tests that we've been doing, there's some point where they say not equal to, less than, or greater than. This next prompt here is basically asking the same thing. Is it a not equal to? It's a two tail. Is it a less than? It would be a left tail. Or is it a greater than, which is a right tail? So we look at our alternative hypothesis. We see a less than. It points to the left. And so we're going to select 1 for left. That was quick. So what do we use again? What's this called? This is test dev. Pardon me? Possibly. You might wonder if a particular data set has a standard deviation that's bigger than something, in which case that would be a right tail test. So this is what's it called again? The test SDev. This is program. And what we have here is our test statistic if we continue or want to continue to use a traditional method, 1.6278 or 9. I guess they usually want 3 decimal places because that's what you compare it to. You compare it to the critical values, which are rounded off to 3 decimal places. More importantly, we have our p-value, which compared to alpha of 0.05 is less. And so what is our conclusion here? So since PV is less than alpha, we reject the null hypothesis. And when we reject the null hypothesis, we think back to our flowchart. You guys have that flowchart memorized yet? That flowchart looks at the first question we asked in that flowchart is that does an original claim contain a condition of equality? The answer is no. So we go down to the last 2 boxes, and then they ask, did we reject the null hypothesis? The answer is yes, and so it's going to be that 3rd box down, which is to support the claim. So let's try to see what choice we would make here. since H1 is rejected, okay, we never reject or fail to reject a null hypothesis. So let's use a red pen to cross that out already. So this isn't going to happen for us. When we're doing a hypothesis test, it's always trying to reject or fail to reject a null hypothesis. So anything that says about rejecting or failing to reject an alternative hypothesis is out of the question. So the other two is that sigma, the null hypothesis is not rejected, the null hypothesis is rejected. So it's the one that is rejected. The variation time is less. It's less than the standard deviation is less than 1.7 that they have there, which is supporting our claim. So I would pick C for this problem at least. So I don't know why they decided in this chapter or in this section to have all multiple choice. I don't know if you guys looked at the homework yet, but it's all multiple choice, or the hypothesis testing. They don't ask. Kind of nice, huh? They don't ask. Well, except for this one. In general, they don't ask for the p-values and things like that.
They sometimes just have like different parts. So you start testing like you do some multiple answers.
Yeah.
And then
After that, if they
you have
start.
to figure out.
Yeah. Okay. But I've noticed these last ones because I was doing these as examples. Like I can see down here if they have more parts and stuff, and they don't have any more parts. So it looks like number 2 is the only one that probably probably has that multiple parts. So this would be worth practicing. And even if you get it right, after you get something right, you can always do another similar problem just to check yourself and make sure that you're understanding it, if you have time. Time. Okay, so those are 3 programs that I think are worth using. That's not built into our calculators, and so I think if you can get used to using them as you're doing these homework assignments, that would be great. So that if you come up with one of these problems on the quiz or on the test, that you'd be able to knock it down. But most of the other ones we have built-in programs for them, which is nice. So that's good. All right, any questions? We're going to dive into Chapter 9. Ready? No. So Chapter 9 homework is due on Monday, and we're not going to meet between now and then, so I figured we need to talk about it. So the rest of Chapter 8 is recorded already online. And just to let you know what I did, so you can go to that YouTube link at the top of our web page, but I put the
Let's do a problem from section 8.
This is supposed to come up with a whole list of other ones. This is just one of them. All right. I have to find a way to... I suppose if you just Google Math 200, and here's the next one in my list. Oh yeah, I guess so.
Let's do an example.
So this is the page that I was hoping would pop up, because this has a playlist. Oh, but there's other stuff in here too. I might need to fix that. Okay. Anybody use YouTube and upload videos and stuff like that? You guys know how to use channels? Yeah, but there's other stuff here that I wasn't interested in showing you. What? Yeah. All right. Any case, you guys can mess around with that. So our task today is to try to cover as much of Chapter 9 as possible. And I think I told you that Chapter 8 is really vital to the rest of the semester. And that's because everything that we do from now on is going to be a hypothesis test and a confidence interval. And if you don't understand the hypothesis test business, then this is going to be a little bit difficult. Now, I know we just talked about it on Tuesday, but it's really, we're going to talk about the same thing, doing the same thing, except with a slightly different scenario. And so that's what's happening with our with our course now. Okay. So the thing about these, all of these will have for us nice computer or calculator commands that would make things really easy. That's the good news, but bad news is, I don't know if it's bad. You still need to understand what it is we're doing. So also another nice thing about this is that this essentially has 3 sections that we're gonna go over, and the nice thing about this is that there's no section on the standard deviation, which for us it seems to be the most complicated one because we had to do table A4 and some chi-square distribution and stuff. So the good news here is that there's no chi-square distribution. All right, so let's take a look at this chapter. The overview in this chapter is that we're going to be using the same, like I told you, we're going to be using the same information that we've been using in Chapter 7 and Chapter 8. Chapter 7, confidence intervals, Chapter 8, hypothesis testing. But this time, we're going to use it to compare 2 different populations. So they say 2 samples. Essentially what we're doing is we're getting a sample from 2 different populations to make our comparison. And the first one is going to be on proportions. Like everything else that we've started, the first ones were all proportions. And as we start these things, we have this idea that we come up with some requirements, and then we're going to come up with some formulas, and then we're going to run through that same process of finding confidence intervals and hypothesis test using those new formulas. All right. The requirements ask us that we have proportions from 2 independent samples, and the samples again are simple and random. So independent samples, a popular example would be males and females. So those are 2 distinct samples. Another one could be, like for me, the things that I always use an example is that the students in my online class versus students in the face-to-face class. So those 2 samples are distinct, or those 2 populations are distinct, and then I would be grabbing samples from each of those. The idea is that they're supposed to not be from the same population. So the way they they put the headers on this chapter, and each of these sections, they say finding the proportion or finding the difference in the proportion between two different samples. But I actually think they really come from two different populations, and you're getting a sample from one population and another sample from another population. So the two populations, I think, are distinct. So from each of these two samples, we have the number of successes is at least 5. The number of failures is at least 5. That's that business where we have NP bigger than or equal to 5, NQ bigger than or equal to 5. That's just to make sure that that it's a large enough sample so that we don't have to worry about skewness. And I put NP and NQ, but really there's two of them. So when we start looking at the notation, you'll see those same variables that we use for the proportion in Chapter 8, except since we have two populations, one of them is going to have a sub 1, the other one is going to have a sub 2. So on our next page, this is all the notation that we're going to use. So it's basically the same notation that we used before. The P is for the population, the N is for the sample size, the X is the number of successes, and then X1 over N1 is going to be P hat 1, which is a sample proportion, and then Q hat 1 is the 1 minus P hat 1. And probably should include Q1 equals 1 minus P1. So that's nothing different. The difference is that all those have sub 1 because for the second population, we'll just have a sub 2. So we have the same thing for the second population, the same ideas. You got the sample size, the number of successes, and then the proportions, except they have a sub 1 and sub 2. That's all. So now that we have the notation, the next thing to do is come up with a formula. Oh, before the formula, yeah, more stuff. Before the formula, what they did is they, so from one sample, we have the number of successes over the total number of people in the sample or things in the sample. From the other sample, we have the number of successes divided by the total number of people in the sample. What they did here in this whole idea of pooled is when they say pooled, they're combining the two different samples together. And so this is a total number of successes for both samples. And this is a total of both samples. Oops, I meant to say total number of successes for both samples. And then total for both samples. So you'll see the word pooled again a little bit later on. And the idea behind pooled is to put things together, put the two samples together. So what happens is that it turns out that having a pooled sample will give us a more precise account of using our formula. Turns out that if we pool them, our formula is going to be more effective. So our formula then will probably be using this pooled sample business. Oh, and there's also Q bar. So, we're going to get to the formula finally. So here's the formula. Now, I'm sorry, I should have split this up in the slides. This is the test statistic down here. This first part is your null hypothesis and your alternative hypothesis. Now, they're missing, and they intentionally left out all the possibilities. So we have three possibilities. We only have three combinations for the null and alternative hypothesis, and they look like this. This is our first option, where it's really based on your alternative, right? Whichever way your thing is pointing, it's going to give us your information about the tail. And they intentionally left this top two out here. The P1 is bigger than or equal to P2, and then the P1 is less than or equal to P2, because they figure that this equality can and should replace those other two. And so you can make these things disappear if you want, or you can leave it there and say this is equivalent. So those two are equivalent to just using the equal sign, because when we say that the null hypothesis has a condition of equality, that's essentially what we're saying, is that they're equal. And saying your alternative hypothesis as being less than or being greater than or not equal to, then we can assume that the condition of equality would be just the opposite. All right, so this is just like all the other ones that we've had. You know, we have possible three combinations for the null and alternative hypothesis, and then now we have this test statistic. Now, according to the null hypothesis here, P1 is supposed to be equal to P2, and that's really what we're testing, right? We're really testing the null hypothesis. If you look at that formula, we have P1 minus P2. So if P1 is supposed to be equal to P2 in our assumed hypothesis, in our null hypothesis, what can you say about P1 minus P2? Should be 0, right? So that's what it's going to turn out to be. For us in this class, since our null hypothesis is always going to look like this, P1 is equal to P2, our P1 minus P2 is always going to be 0. So if you were using this test statistic by hand, by the formula, P1 minus P2 is always going to be 0 for us. The only time it wouldn't be 0 is that if you want to say in your null or alternative hypothesis, if you're comparing P1 and you're going to say it's going to be 3 times more than P2 or something like that, or it's 5 percentage points more than P2. If you had some weird claim like that, then that would be a time where this might not be equal to 0. But let's just say in this class, we're always going to be dealing with P1 being equal to P2 for our null hypothesis. So let's just stick with that. Okay. So as part of that formula, we have the p-hats, and p-hat was already explained a couple of slides ago. And then we also have the p-bar, the pooled proportion, and that was explained a couple of slides ago. And so that's just what this is. All right, I think it's time to do a problem. So let's take this. Should we take this, or should we? Let's do a homework problem. So by the way, if you look at the slides that will be posted, or even before this was posted, the slides that they have, you can see all the answers, the results there. So I won't do this one. Instead, we'll do a homework assignment. That'll kind of keep you guys going or get you guys started with your homework. This would be 9-3. Whoa, there's a lot. You guys better get started with your homework. Wait. This doesn't look right. Oh, we're supposed to be doing 9-2. Sorry. That's still a lot of problems. All right, let's do this one. So, section 9-2. So this is our problem. Tax returns include, so this is a lot of times, or some of the times, they'll have a nice table that's set up for you, and when they have a table, then that makes things easier for us to pull out the values that we want. Here, there's no table, it's just a big long paragraph, and so you have to be careful about the numbers that they put up here, and try to be able to use them appropriately. And the first thing that we're probably going to want to do is, before we figure out the claim and things like that, we want to decipher what's given. And so if you know that this is a two-sample proportion problem, let's get this set up with the first sample and the second sample set up. And then here we're going to need to fill this in with n and x and maybe p hat or whatever else we might need to come up with. And you have to identify what your first sample is and what your second sample is, and then from there try to figure out those values. So let's read the problem. Tax returns include an option of designating $3 for presidential election campaigns. In a simple random sample of 450 tax returns from 1976, 26.2% of tax returns designated $3 for the campaign. In a sample of 400 recent tax returns, they don't say what year, but I guess we assume recent means a couple of years ago, the returns designated, or 7.9% designated $3 for the campaigns. And then here is the statement of the test, hypothesis test. Use a 0.01 significance level to test the claim that the percentage of returns designated $3 for campaign was greater in 1976 than it is now. So now being the recent. So we can identify which one should go which. And so let's call the first one the tax returns from 1976, since that was the first set of values that was given. And then tax returns more recently. And so let's highlight. Maybe if we use two different highlighters, 450 and 26%. Where first of all, you see $3 right there. That's a number, right? But in your mind, you should just throw that away. That's impertinent. That doesn't have anything to do with our problem. So 450 and 26.2% are related to 1976. So 1976 is our first population. 450 is what? N. And this time, instead of just calling it N, we'll call it N sub 1, because this deals with our first population, N sub 1. Now 26.2%, what is that? P hat, right? It's not X, and we will need X. So let's call it P hat 1, and that's 26.2%. And we can figure it out now, or we can figure it out later, but let's figure it out now. Given those two pieces of information, you know how to find X, right? What do? Multiply. So make sure you move the decimal. So 0.262 times 450 is what? So it's 117.9, and we want to round to the nearest whole number. So that's 118. All right. So remember, your calculator doesn't like it when when it is expecting a whole number. And if you type in a decimal, then it's going to complain about it. It's going to give you an error. So those are errors that you don't need while you're taking a test, because you just kind of panic and stuff. Fortunately for you guys, I'm here. So if you panic, you just tell me what, I have an error. And I'll say, oh, sorry, too bad. But those are usually the errors that come up is because of that. All right, now let's see what we can pull out of the other one. So the more recent tax return, and there's only 400 instead of 450, and only 7.9. You might think that, clearly there's more in 1976, so you just want to call it a day and say, yeah, there's just more then. But the idea behind these statistics is that just because there's more on the sample that you're given doesn't mean that that's going to be true for all the time. And so that's why we go through this process. So it looks like we have an N2, and then it looks like we have a P2 hat. And so you should be able to give us the X2, which is what? What is it? 32.6? 31.6, which rounds off to 32. All right, this is our prelim information that we have to try to make sure that we get before we jump into the step-by-step process for the hypothesis test. So now that we got them, we can look at our problem again and basically highlight what you think the claim is going to be And then also use the fact that they're using the word test and significance level. You know that this is a hypothesis test. Percentage for us should kind of relate to proportion for most cases. So you know that this is a proportion instead of a mean or standard deviation or something else. So let's start off with our claim. So our claim is that the percentage of returns that designated $3 for the campaign. Oh, I don't want to write all this stuff down. Designated $3 for campaign was greater in 1976. Now, the percentage, replace that with the word proportion. So the proportion in 1976 was greater. How would we write this claim in mathematical symbols? Proportion, we're going to use P. Proportion for 1976 is going to be labeled as what? P1. We've called that 1. We've called that our sample 1. So the proportion related to 1976 would be called P1. That would make the proportion for the more recent year called P2. And in my null hypothesis, I'm going to want P1 to go first. That's just going to make things easier for us. What is the symbol that goes here? Greater than. Okay? All right. We're all set. We're done. No, but all right. So since this is a summer, the compressed schedule, usually I do the 8-step process a few more times and stuff, but I'm going to not do the 8-step process anymore, but you should still think about continuing to practice that. But I'm going to tell you what I really, really am looking for in this type of problem. I will be looking for your null and alternative hypothesis. I don't care how you get it. I think the first 2 steps in the 8-step process help us figure out the null and alternative hypothesis in a systematic way. But really, if you can identify your claim, you can figure out where that claim goes, and then you can fill in the other hypothesis. So this one does not contain a condition of equality. Clearly, that's going to go into the alternative hypothesis. Then I know what goes in my null hypothesis, right? So it's P1 is equal to P2, or you can use that less than or equal to if you want. As long as H naught, the null hypothesis contains a condition of equality. So this is the first thing that I want to see in your hypothesis test problem. The next thing I'd like to see would be the test statistic and the p-value, if you're going to use a p-value method. If you're not going to use a p-value method, then the next thing I want to see is the test statistic and then critical values. So basically whatever important parts that will come up. Now, our step 4 in our 8-step process is figuring out the alpha. So that alpha is usually given, and if it's not given, so I don't need to see that written down. So the next thing I would like to see is your test statistic and your p-value. So for that, since now we're going to use our calculators, I'm going to want you to write down what calculator command you put in. So let's take out our calculators. And let's go to stat and tests. Can you guess which one? Two? Did you guys went to Frank's office, or you just figure it out? Figure it out. Good. There's two of them. Prop for us has meant proportion, and so that's what prop is. And it's a test, so it's a z-test. So 2 prop z-test is what we're looking at. So you hit enter, and then it's going to ask you for x1 and n1. If you labeled it correctly from the beginning, then all you're doing is you're copying off your paper. So x1 is 118. Our n, or sample size for the first one, is 450. Our x2, it's 32. And our n2 is 400. And then the same thing, right? Except now we're looking at P1 compared to P2 instead of P compared to P naught or whatever it was back then. And if you did your alternative hypothesis correctly, you'll see that very same symbol pop up as one of your choices. So we have a greater than symbol, and we want to let our calculator know that we're going to use the right tail test based on what we have as our alternative hypothesis. So let's press enter, calculate. Now, whenever you see an arrow down, remember there's more stuff down there, but the more stuff down there is information that you already know, so that's not really that relevant or important. The other thing that pops up here, which is good verification for us, is the P hat 1 and P hat 2. P hat 1 was 26.2%. That looks like it coincides with what we have. And 7.9, this went to just 8%. So that looks like it's close enough, so we'll buy that. It looks like we did our calculations correctly and everything is working out according to plan. So obviously you can't just take screenshots and put it on your test, right? So what do I want to see? I want to see that you use a 2 prop. This is the next step. You use a 2 prop z test. And if you're not sure what I want, then write everything down. Yeah, maybe. I want you to write down your test statistic. And it really helps if you write down your test statistic using the appropriate distribution. In this case, we're using a z distribution. So z, and then you can pull that out here too. Z is equal to 6.9558. Let's call it 89559. That's your test statistic. And then there's a lot of p's around here. There's p hats, there's p bars, and there's all kinds of. But what you want to look at is your p-value, and because there's so many p's around here, I'm going to want you to call the p-value PV. And PV is it 1.7? 0 plus. It's really small number. It's 1.7 e to the negative 12, if you want to think about it that way, or 0 plus 0.000, something really small. 11 zeros before the first significant digit pops up. So I want you to write your test statistic and your p-value. So remember, when we first started talking about hypothesis tests, there's 3 major steps, and then that got broken down to 8 steps. The first step is to state your claim or your hypothesis. The next is to test your hypothesis. and then the last is to draw a conclusion. So this is like the first big block, this is the second big block, and then now we're going to draw our conclusions. We're going to make our decision based on the p-value, and you know, when you reject or you fail to reject, I kind of need to know why you're rejecting or failing to reject. So you can say reject the null hypothesis because, or I'm going to say it the other way, since PV is less than alpha, and maybe you want to write down the p-value of 0 plus being less than 0.01 or whatever the alpha was. We reject the null hypothesis. And then we want to write our, this is the very last part, is really the most important part, to convey your findings with non-statisticians, so write it in non-technical terms. That flow chart in your heads, or if you look at it in a piece of paper, does the original claim contain a condition of equality? Does the original claim contain a condition of equality? No, it doesn't. So we go down to the last two bars. Did we reject the null hypothesis? Yes. So we're in that third slot. Sample data supports the claim that and just copy exactly what you wrote down for your claim earlier. The percentage of returns that designated $3 for campaigns was greater in 1976 than recently. So this is the last bit of information that I would like to see on your test when you guys are doing the hypothesis test. So you don't need all the 8 steps if you're used to this now. Okay, but I do need to see the null and alternative hypothesis. I do need to see your test statistic and your p-value, and how do you get that? So how did you get your test statistic and your p-value? Well, we have to make sure that you tell me how you got it. It didn't just magically appear from somewhere. So you use a calculator using the 2-prop z-test. And based on that, what was your conclusion? This rejecting and failing to reject is important, because that's how you make your final wording. You need to know what happens. And then whether you reject it or fail to reject is going to control your final wording, which comes from that chart. Okay? Sound good? It's pretty easy. Yes. So these things should come, the steps, you do it over and over again, you get used to the steps. So the hard part will now, hopefully, the hard part will become what kind of problem you're dealing with. Okay? If you're at that point, then that's good. If you're not at that point, that means you're still trying to figure out how I'm getting all these steps, which means you need to practice. Just practice doing a bunch of these things. And as you're doing the homework, that's easy, because you know what section you're in, right? So, I'm in section 8.3, so I must be dealing with proportions with one population. And so that's fine, and you get used to doing these steps, and you practice, do these steps, and so these steps become natural to you, because you're going to do this for the rest of the term. 2 weeks left they have. So the hard part should be trying to figure out what what it is you're dealing with. And for that, what we'll try to do is one of these days at the beginning of class, once we have a lot of these different types of hypothesis tests figured out, what we can do is we can just grab a whole bunch of problems from different places and then just look at them and then imagine what kind of problem is this? Is this a 2 proportion or 1 proportion? Is this a proportion? Is this a mean? Or is this a standard deviation? So if we go through and walk through that process, we can eventually cure that. I don't know if cure is the word, but we can eventually overcome this idea that it's hard trying to figure out which process we're dealing with. But for now, you're in a little zone here when you're doing, I'm in section 9.2, so I'm doing a 2 sample for proportion. So just go through the steps with a 2 sample proportion. And then later on we'll mash it all up. All right, so let's see. We rejected, we supported the claim. Let's see if we can answer the question. And then I want to go back to the same problem and do another part that's not in this particular homework problem, but I want to do a confidence interval also. So tax returns, okay, since the p-value is, it was close to 0, right? So it's less than a significance level. There is sufficient evidence or insufficient or supporting. So there's sufficient evidence to support the claim. Okay. All right. Since we have this problem up already and since we have all the information up already, let's continue on to this problem, although there's no other parts here. Let's continue on to this problem and let's ask ourselves to find the confidence interval. And then I want to talk a little bit about that as well. And we'll use this information for your confidence interval, and we'll talk about how to write up your confidence interval. Should I copy it? I'll just copy it down. So x1 is 118, n1 is 450. X2 is 32, N2 is equal to 400. And that's all we'll really need from the confidence interval. All right, so for the confidence interval, let's take our calculators out again. And let's go to stat and test. Now the intervals seem to start after 7 here where the z interval goes, but if you keep scrolling down, there we go. 1 prop z int we used already, and the one right after that is 2 prop z int. So let's do a 2 prop z int. And if you had just done a hypothesis test using your calculator, then all the data is still going to be there. All the statistics is still going to be there. That's nice, huh? Let me change the confidence level to 99%. We've been using 95 a lot, but not like it's going to make a difference. And we're just going to get a bunch of numbers that I'm going to write down anyways. Oh, I wanted to take a picture of that. So if you press, go ahead and press calculate, then you're going to get some value or a couple of values. and they throw back the statistics at you, the N and the P, or the P hats. So the way I would like you to write this answer down would be, remember I was being specific about how to write the confidence interval answers. So here would be 0.1184. I think 3 decimal place would be good, but just write down exactly what they have here. But instead of the interval notation with parentheses, I'm going to want you to use a less than symbol. And then this is why I want you to use a less than symbol, because the next symbol is going to tell me whether you're really you know what section we're in and what you're actually looking for. So instead of just one variable like we've had in the past, this is a comparison. This is a difference between P1 and P2. And this is the next one is 0.24604. So you could say that you actually use 2 prop z int for this problem. And then whenever you do these types of problems, it's always good to write down your non-technical terms. This time we're 99% confident that the true difference in proportions, instead of just saying the true proportion is, it's the difference in the two proportions. Between the two samples is, I guess, between 0.1184 and 0.2460. So you can look at how we used to write the confidence interval in words back in Chapter 7. It's basically the same thing. But there is one important analysis here as well when you're doing confidence intervals and comparing two things. And the question is whether this confidence interval contains 0 or not. Does this confidence interval contain 0? And how can you tell if it contains 0? It does. Zach said no. Right? This doesn't contain 0. How can you tell it doesn't contain 0? There's no what? So what number is before 0? What numbers are before 0? Negative. So there's no negative numbers. Okay? So if it contains 0, then one number should be negative, the other one should be positive. If they're both negative or they're both positive, like in this case, then it doesn't contain 0. And that's significant when it doesn't contain 0. Come on. Oh, wow. Oops, this is on the right side. This is 0.11, 0.24. So if you're looking at the difference between two proportions or two means or two whatever, and it doesn't contain 0, since the confidence interval does not contain 0, there is a significant difference between the two proportions. Okay? That means the difference is really big. If it contains 0, then you can say, oh, they're close enough, so there's probably not much of a difference between them. But if it doesn't contain 0, either going too far to the left or to the right, then you can say, oh, the difference looks like it's really big. There must be a significant difference between these two things. Okay? So when a confidence interval for these two samples that we're dealing with in this chapter, when the confidence intervals do not contain 0, then there is a significant difference between those two things that we're looking at. All right? A lot of stuff, huh? Okay, so 8 o'clock, break time. Let's take a little break. We'll come back and we'll try to tackle the means for the next section.